you cool cats and kittens? We're going to go over the exothermic lab, and we'll talk about bond energy and the reaction coordinate diagrams that go with this lab. Excuse me. So recall, exothermic means that energy is being released, it's exiting. Endothermic means that energy is required, or it's being absorbed into the system. Enthalpy is our total change in energy, so if you're losing energy because it's being released, that's a negative change, versus if it's absorbing energy, that's a positive change. Bond energy is our energy required to break bonds, so if you need to break a bond, you need energy to do that, that's endothermic, versus if you want to make bonds that create something more stable and lower energy, and so you release energy when that happens, so it's exothermic. We talked about these two graphs. We have the exothermic graph and the endothermic graph, and they're opposites of each other. Reactants in the exothermic start off with high energy and then release lots of energy at the end. Versus the endothermic, these reactants absorb lots of energy, and then their products are at a higher energy state than they started at because they absorbed all this energy. And from reactant to peak, we have activation energy, which is our energy required to start the reaction. And so our reaction, we have steel wool, we have vinegar, and we have thermometer. And so when you mix the steel wool and the vinegar, the vinegar breaks down the coating of the steel wool, and the iron is now exposed to oxygen. And that oxygen and that iron start combining to form rust, also known as iron oxide. And so our first question is, what's this chemical formula going to look like? We have iron metal, oxygen gas, and iron 3 oxide. The metal indicates it's going to be a single atom. Oxygen gas is one of those Brinkelhoff twins. It's a diatomic element. Di means two. Atomic, 2 atoms, so we'll have O2. The iron 3 oxide, the 3 indicates the charge on the iron, so we'll have to think about the charge of the iron versus the charge of the oxygen. Here's our single iron, our 2 atoms of oxygen gas. We said iron 3 has a charge of +3, and oxide is oxygen has a charge of -2. So if iron is +3, oxygen is -2. If we want them both to balance out to 0, we need 2 irons and 3 oxygens. So that would give us letter C, iron O2 plus iron oxide. Since those weren't balanced, let's balance it very quickly. Anytime we have 2's and 3's, to make that balance, we want to make it 6. So 2 times 3 is going to give me 6 oxygens. It's also going to give me 2 times 4 irons. So if I want 6 oxygens on the other side, I need 3 times 2. And to balance out the irons, we need 4 irons right there. So now we want to know the total energy in the bonds. We know that enthalpy is our reactant bonds minus our product bonds. We know that the iron has 0 bond energy because there's no bond. We know that oxygen, the double bond, has 495 kilojoules per mole. We also know that the enthalpy is negative 824 kilojoules. So now this is just a basic algebra problem. Here's what it looks like in a picture. Here's the iron with 0. Oxygen gas with 495. We don't know the products. The enthalpy is negative 824. We're going to plug that into this formula right here. Enthalpy is the total bond of the reactants minus the total bonds of the products. So we get negative 824 is equal to 0 plus 495 minus x. We do the algebra through this, add these up, we get 495, subtract it, we get negative 119, make them both positive. 1,319 kilojoules per mole is our total product of bond energy. So that means if I want to break these bonds, I need 1,319 kilojoules to do it. So given that our enthalpy is negative, and that we know that it's releasing heat, because it's negative, that would mean it's exothermic. And if the surrounding is absorbing all of this heat, the temperature should increase. So we're going to need vinegar, steel wool, and a thermometer. I soaked my steel wool in the vinegar for like a minute or two. I stuck it in a jar, I added foil on top to keep the heat in, and I stuck the thermometer in. We started off at 80. After a minute, the temperature went up to 90, and after 2 minutes, the temperature went up to 100 degrees. If we look, the jar is very steamy, indicating that those water vapors are becoming gas, and then they're hitting this cold glass, and they're condensing on the glass because we can see these little water droplets. When we pull the steel wool out, there's this brownish reddish color indicating that rust was formed. So the purpose of this lab was to look at exothermic reactions, which means that heat was released. This also means that because energy was released, we have to be making bonds and making more stable products. And as this energy is being released, our surrounding temperature is increasing because it's absorbing all of this high energy coming off of our system. We use vinegar, we use steel wool, we recorded with thermometer, and we covered it to prevent heat loss. Our balanced equation is here. We have our iron metal reacting with oxygen gas. We can consider vinegar a catalyst. Again, we'll learn what that is in a little bit. And this iron 3 oxide is produced. Now let's talk about reaction coordinate diagram of the system. So our steel wool is here. It's got all this oxygen around it, and it starts binding with the oxygen, and it starts releasing all its energy. Our steel wool is releasing energy until we get these low energy rusty products. And because our system is releasing all of this energy, our surrounding is getting warmer because it's absorbing all of these high energy particles. So our reactants, we started off with iron and oxygen, and we produced iron 3 oxide. We saw the steel wool turn this reddish color because it was forming iron 3 oxide, which is rust, which has a reddish brown color to it. We know the enthalpy is negative, which indicates an exothermic reaction. And in an exothermic reaction, the surrounding gets hot. And that's because our system is releasing energy into the surrounding, and that surrounding temperature increases, and that's what we measure with the thermometer. The end.